Hello, everybody. Welcome back to the Doctors In podcast. I'm your host, Dr. Nadia Sabeh, and this is our special series, What Plants Crave, where I'm talking to growers and scientists about the plants they grow in greenhouses and indoor farms. My guest today is Dr. Fatemeh Sheibani, who's a postdoctoral researcher at Purdue University's Department of Horticulture and Landscape Architecture. She has been leading research efforts on lighting efficiency and co-optimizing lighting with other variables, such as carbon dioxide, along with Dr. Carrie Mitchell. Much of her research has been in support of Optimia, which is a USDA-supported specialty crop research initiative focused on optimizing indoor agriculture to increase its sustainability and profitability for vertical farming. Fatemeh, it's really great to have you on the What Plants Crave podcast. You know, the research that you've been doing in these recent years has been really interesting, and I'm really excited to talk about it. And your thoughts specifically on how lighting efficiency and energy efficiency in a bigger picture can be improved in vertical farming. We know it is a major challenge for indoor farming, and so I'm really excited that you are focused on improving efficiency.
Hi, Nadia. Thanks for having me. Let me take one step back and give you some information on a bigger picture of vertical farmings. As you know, under the umbrella of controlled environment agriculture, vertical farming is a relatively new industry with only a few decades of history. It's considered as one of the expensive industry because of the high capital expenses and operational expenses, but still it has a lot of advantages. For example, we can produce more in less area with significantly higher water use efficiency, less harm to environment. For example, by minimizing the fossil fuel transportation that was needed initially to transport produce from other part of the country, which is mainly the production sites. But still, these industry, we see in the news that there are new vertical farms establishments in all over the world. And but on the other hand, there are news about some of them ceasing operation and filing for bankruptcy. So the question is why this is happening. In one hand, we have an expensive industry with high operational and capital expenses. On the other hand, it's growing rapidly. So talking more about capital and operational expenses, there are two main capital expenses. One is the expensive land or property in urban areas, which is mostly the production site for vertical farmings. And another is the initial high cost of LED installments. Two of the main loads of operational costs are labor and electricity costs for lighting and HVAC. That's the main reason why in the past few years here in Mitchell Lab at Purdue University, we are focusing on how we can improve energy utilization efficiency through having a better lighting utilization efficiency, and how we can make one step forward toward the profitability of vertical farming industry.
So that basically answers, you know, kind of the first question I was going to ask you, which is why lighting, and specifically the energy use efficiency or energy utilization efficiency of it. What does energy utilization efficiency mean, and how does it different from other metrics that we might think of around lighting, like photosynthetic, photon efficacy, or even just energy efficiency in general?
That's a great question, and I would prefer to answer the second part of your question first. I want to define photosynthetic photon efficacy, which is basically by definition a micromole of photosynthetic photon output divided by joules of energy input. And I would like to bring another term of electrical efficiency to your attention, which by definition is the ratio of radiant power output by the electrical power input. We all know that significant advancement has been made to make LEDs or light emitting diodes as the sole source of lighting, to make them more electrically efficient and also to improve photosynthetic efficacy of them over the last few decades. And engineers have done a great job in that regard. Right now, we do have very efficient LED lighting system. But the question is, do we use these efficient LED lighting system wisely? In some cases, the answer is no. We are wasting all those efficient photons very easily. And we should reconsider the whole approach, and we should think about it carefully, how we should use this lighting system very efficiently.
So can I hold on? So when you say that the LEDs or the source of lighting is efficient, are you saying that the amount of power it puts out versus the amount of power you put in is high, that it's, I don't know, just I'll throw out a number, greater than 50% or close to 100%, or, it's a percentage, right? When you're saying that an LED is efficient, that's what you're saying, right?
Yes, that's exactly true. So there are theoretical values for electrical efficiency and photon efficacy of LEDs that we are very close to the theoretical values. So there is a maximum value that we can reach, and we are very close to that. That's why LEDs are very efficient, the best choice of lighting, and probably the only choice of lighting for indoor agriculture.
So when you say it's almost reached the theoretical limit, so what is the theoretical limit of efficiency for an LED? Is it 100%, 90%?
So I don't know if it's a good idea to define them as percent, but there in the literature there are specific values that some scientists are focused on, and they report that. And then they do have a bunch of LEDs from different companies that they have been communicating or working with. So they report those values from the companies, and one that they've calculated to be theoretical values, and how these values are matching and getting close. So then we do have very efficient LEDs these days. The question is, what else we can do? We do have very efficient LEDs. We are not using them wisely sometimes. So is there anything else that we can do? That's when we started to think about physical properties of LEDs. We decided to investigate more about LEDs design and properties. And we started with this whole idea, and then we had different approaches, and we worked on different projects. So I want to talk a little bit more about lighting use efficiency that you mentioned. When we tell lighting use efficiency, it can include different aspects of lighting. But to make it easier for ourselves to understand, I use another term, canopy photon capture efficiency, which is basically a fraction of emitted photons intercepted and used by plant leaves. So the better that we can improve canopy photon capture efficiency, we can enhance energy utilization efficiency, that we define it as the ratio of biomass produced per kilowatt hour of energy, and ultimately we can improve lighting use efficiency. So all of these terms are connected somehow, and but at different levels. So for example, when we talk about energy utilization efficiency, it means gram fresh or dry biomass produced per kilowatt hour of energy that we are expending on LEDs. And it is linked to the light use efficiency, because the higher the energy utilization, the efficiency, the better the lighting efficiency will be. So all of these are connected.
Okay, so we have an efficiency associated with the light fixture itself, the light source itself. And then so we're reaching sort of a limit on that, and how many photons per joule we can produce with LEDs or with any of the fixtures that we've been using in horticulture. And so now what you're doing is you're now moving away from the device itself to now the actual canopy, and moving into the room, and how the plants are utilizing the light energy that's being emitted by those components, by those light sources.
Yes.
Okay. Okay. So it's kind of a cascading effect. We have a really high efficient light. Now, how do we use the light that's actually being emitted by those lights?
Yes.
So are these then more cultural practices, or are they more, you mentioned physical properties of the light. So is it like adding reflectors and things to lights?
So it's a combination of different things. It's both the cultural practice as well as understanding more about the design, the initial design of LEDs, because we are plant scientists, we are not engineers, we haven't designed these LEDs. Engineers are designing LEDs, and we are using them for the purpose of the indoor plant production. But what we did, we digged into the design and how these LEDs are being built. And is there something else that we can take advantage of LEDs rather than just being efficient? Because they are very efficient, and we know that, and there is nothing more that we can do about it. But is there something else that we can take advantage of that? And I will explain later as we get to more focused area. What I mean,
That's
physical properties.
I mean, that's just really interesting, because I guess I think of I haven't really thought about the physical properties of the light, of the diode or the fixture itself, and how it might affect, I guess, the distribution of light. And I think that's what a lot of your work has been. So let's talk about, let's start diving into that. So a big chunk of research that you've been working on, and that you've published recently, is a study looking at close canopy lighting. So that's I don't, did you coin that term?
Yes, this is the term that this is the term that we have based on the approach that we have. We made that term ourselves.
I love that. That's awesome. Okay, so how does that compare to what we would typically think of traditional overhead lighting?
That's a great question. So closed canopy lighting was our first approach that we have investigated, and we characterize these closed canopy lighting to enhance canopy photon capture efficiency by minimizing photon spillage beyond the cropping area. So when we think about LED design, first generation of LEDs were designed for the human perception and for other indoor activities. And the illumination pattern of those LEDs is very close to the Lambertian, they call it, or cosine weighted distribution, which means that most of the illumination occurs within a 120-degree angle. So keeping that in mind, for example, in other words, if we consider LED as a point source of lighting, it's like a sun that's radiating 360. And when we mount that LED engine on a surface, on a flat surface, then the radiation, the illumination pattern would cut down to half, which is 180.
Okay.
And then following the Lambertian or cosine weighted distribution, which basically has a lot of physics and mathematics formula behind it.
Of
And
course it does.
I don't understand most part of that. And I'm not an engineer, as you know. I'm just learning through self-education, reading literature, and communicating with engineers who design LEDs. So these are what I've learned. So when these LED design are following Lambertian, most of the illumination occurs within 120 angles, almost 80%. And the rest is out of that. I mean,
Hmm.
you consider plus minus 60 degrees, which is 120 degrees. Most of the illumination is within that, and the rest is out of that. But another property of LEDs that are designed based on Lambertian distribution is that they are very bright in the center. And as they are getting away from the center of illumination, that brightness would fall off. So given that, when an LED engine is energized along with other LED engines that can be in a tubular type, there might be tubes of LEDs across or along the benches, or there might be bulb type layouts on the benches above plants. And when all engines are illuminating at 120-degree angle, a new illumination pattern is shaped that we do not know too much about it because more investigation is needed. We need to illuminate different LED engines with different separation distance between engines themselves to decide the illumination pattern and lighting map. This is something that mostly those companies that they provide LEDs, they do that. They create a lighting map, and I think they decide how many, for example, fixture, a cropping area, or a specific bench needed, and how much should those growers invest. But we want to bring that into growers' attention and also plant scientists about these basic design of LEDs. So,
Can I ask a question real quick on the Lambertian distribution? So if I'm thinking about these 120-degree angles, and this is where probably people would love to have a video because they could see us like drawing this really wide V shape, basically coming from the top of a rack maybe, and then spreading out across the plants down below. So just imagine me, everyone. I have my fingers pointed together, and then I'm spreading them apart to illuminate the plants down below. Um, so if you have LEDs, right, a lot of times they're in columns or in rows or in a grid shape pattern, I guess you would say. Uh, if you just had one LED doing that 360-degree, 120-degree, right, it would be in a circle, I imagine, right? If you just had one LED, it would illuminate a circle at 120 degrees, a cone, basically. Is that right?
yeah.
So uh you would get an even distribution of that light at whatever height it was from that one diode. But once you have another diode next to it and you have overlapping light waves, is that the portion that is overlapping, is that a higher intensity than the portion that might be directly below each LED?
That's a great question, and I do not know the answer, which I
Okay.
believe that more investigation is needed because We do not know too much about the new illumination pattern that is being shaped when we have all LED engines energized. We are talking about a single one, but we don't know how this whole pattern would change when all of them are energized. But you brought a very good point of this distribution and the overlap. When we set our lighting in the vertical farms, they provide LED to the edge of the benches to avoid edge effect. But there is the point that tremendous waste is happening because of those wide angle on the edge of the benches, and all those photons are falling on the ground.
Yeah.
That's basically when closed canopy lighting comes to picture. As we reduce the separation distance between emitting surface of the LEDs and crop surface, the chance of escaping obliquely emitted photons from the cropping area is getting less and less. This is how closed canopy lighting can specifically enhance canopy photon capture efficiency.
Interesting. Okay, so you did this closed canopy lighting study. So what were the distances that you tested the lighting away from the crop? And by the way, I guess we should mention what crop you were also studying for this research.
So we used red oak leaf lettuce, rushi, as a model plant. And for this specific study, we considered baby stage of development, which was 15 days cropping cycle from seed to harvest. We developed our own lawn of baby green system. We didn't want to plant like single plants inside different pots or plug holder. We create a combination of coco coir perlite in a 10 by 20 inches tray. And we had a specific number of seeds in that, I think 84 seeds in that tray. And by day 15, which we considered as the baby stage of development, the canopy closed, which means that we used all photons very efficiently. Definitely, we had some loss during the earlier stages that there was no plant there, but the moment that plants start to develop and use those photons efficiently, and then by day 15, we harvested the whole tray. That's the growing system. And we considered 40 to 50 centimeter, which in case was 45 centimeter as the standard separation distance that is being used in vertical farm setting as our control. And we have three more distance of 35, 25, and 15 centimeter separation distance between LED emitting surface and crop surface.
Wow. Okay, I want to make sure I understand the cropping layout. So, were you illuminating the plants from day 0 to 15 and then harvesting, or were you growing the plants to day 15? So you had kind of, you call it a lawn. I would say some of our cannabis growers might call it a sea of green. And at 15 days, that's when you would start the study and then look at it from, say, day 15 to day 30.
No, the study started on day 0, which was the day that we started the seeds, to day 15.
Got it. Okay. So, and then you had these 3 different distances of the LED lights above the canopy, or where you thought the top of the canopy would be. How did you know where the top of the canopy was going to end?
And so that's a great question. Before we start an experiment, we always have some trial with with a small scale.
Okay.
Start the plants to see the level of the canopy, how high it would be, and then we need to place our spectroradiometer in that level to adjust the lighting system and create our lighting map.
Okay. Okay. Fair enough. Fair enough. All right. So what did you find?
So, in the design of the closed canopy lighting in general, we considered dimmability of LED as an factor. We designed two scenarios. In the first scenario of closed canopy lighting, as the separation distance, the vertical separation distance between light emitting and crop decreased, we dimmed them down. So as the result, we have same intensity of light at closer separation distance, but less energy was expended.
Oh,
That
so that's really interesting. So it's not like the plants are receiving more photons simply because the same light fixture is closer to it. You're just trying to get those photons closer to the plants or the same number of photons closer to the plants?
Yes, that's the first scenario. The same number of photons was received by plants at closer separation distance, but less energy was needed. In the second scenario, without dimming LEDs down, we brought the light closer to plants, which resulted in significantly higher PPFD or photosynthetic photon
Yeah.
flux density with the same amount of energy. That's the key. So in the first scenario, we call it energy efficient strategy. We saved a lot of energy because as we dim them down and get closer to plants, we expended less energy on LEDs. On the second scenario, we keep them at the same intensity. We just physically bring them closer to plants without dimming them down. Again, we had high intensity of light, significantly higher biomass production, but with the same amount of energy. We call it yield enhancement strategy, the second one.
Okay, so in the first scenario where you're dimming the LEDs as they get closer, how do you know how much to dim? Like, is it linear? Like,
So we use a spectroradiometer as our standard goal because a spectroradiometer is the device that it can sense both intensity and a spectral composition. We had a combination of red, blue, and green, which we want to keep these compositions same at all separation distances. So a spectroradiometer is a device to help us to measure intensity at different places under our lighting fixture.
so if at 25 centimeter, so would the dimming be 0% at 25 centimeters?
No. So
It was 15, 20, and 15, right? I'm
so
sorry, 25, 15.
our
I
control.
can do this. Okay, go ahead. You explain it since I can't get the numbers straight.
So our control was 45 centimeters.
45, thank you. Okay.
This is the standard typical separation distance that is being used in vertical farm setting. And when we dim them down, let's say that at 45 centimeter, the PPFD or photosynthetic photon flux density was 250 micromole per meter.
Okay, thank you. Yeah, yeah. Real numbers.
Okay, and then at 30 centimeter, we dim them down, we get closer, but still we received 250 micromole of light. At
Okay.
25 centimeter, it was the case, 250 micromole of light, but again, less energy was expended because we are getting closer and closer, and the light is getting brighter and brighter if we
Mm-hmm.
dim them down. And then at 15 centimeter, again, we had the same intensity of light, but less and less energy was used or expended on LEDs. So same biomass, fresh and dry, was achieved under all lighting treatments, while we use significantly lower energy at closer separation distance in the first scenario.
Okay, so I guess what my real question is then, Fatemeh, is by what percentage did you dim? If 45 centimeters is theoretically 100% light output by the LED, by the time you got to 15 centimeters, were you dimming it to 50%, 30%? Like,
I do not have a number, but I think 25% would be safe.
yeah. Okay. Because I'm just wondering, right, if I related that to the energy input to the LED, right, and I went from 100% to 25%, then I'm, reducing my energy use by, what is that, 65% or something like that.
Yes.
So that's why that's a really big number
Yes,
by going from 18 inches to 6 inches. By the way, but 45 centimeters, 15 centimeters. Yeah,
I know.
for my American listeners.
Yeah, that's true. Yeah, we need to deal with journals and they
You're right.
it's better. So yeah.
Exactly. Okay, so that's really big. Okay. Um, and you got the same output. So that's good to
Yes.
know. You didn't change anything about the fixture except its distance.
Yes.
Okay.
And dimming them down. Yeah.
Right. Okay, so second study is now you're just going to keep them burning at a high intensity and bring them closer to the plants.
Yes. So we started at 45 centimeter, 250 micromole per meter square per second of ppfv. We brought them down to 35 centimeter and measured the light using spectroradiometer. Let's say that we reached around 375 or something similar to that. I do have all those numbers in my paper, by the way. And then as we get to 25 centimeter, we reach to higher intensity, and at 15 centimeter was the highest intensity of 400, close to 400 micromole per meter square per second. So basically, we expend the same amount of energy on all LEDs, but we have higher and higher and highest intensity, and we expected to have the highest biomass at the closest separation distance, which we did. We had the highest biomass at 15 centimeter separation distance.
And so, I mean, I guess that's not super surprising that, right? That's kind of the trend that we would expect. Just out of curiosity, I mean, with the red oak leaf lettuce, um, has anyone found the limit to how many micromoles the plants stop growing or stop receiving all those photons and using it for photosynthesis and growth?
That's a great question. We noticed that there is a gradient of color in the pigmentation development as we get closer to plants. We had higher intensity of light and higher absolute amount of blue, which brings all those pigmentation out. That's why those plants that were under the closest light were totally red compared to the one that was grown under 45 centimeter separation distance, which at the baby stage, we didn't have any issue of like tip burn or any other like physiological issue. But I think if we wanted to grow them longer, that was definitely an issue. That's when it's time for us to play with different ratio of waveband. We may need to reduce the amount of blue in the light recipe, which we kept it close to between 5 to 10% of the total photon flux density, but we may need to reduce it even to lower. But I wanted to mention that we used energy utilization efficiency as a parameter that we measured fresh or dry biomass produced per kilowatt hour of energy at the end of the cropping cycle. And at 15 centimeters distance compared to 45, which are the two extremes, this energy utilization efficiency was doubled for both scenarios.
Both scenarios?
For both scenarios, because in the second scenario, higher biomass is achieved, but the same amount of energy is being expended.
Oh, interesting.
Yes, that's very interesting.
So the biomass was the same, but you reduced the energy by 2 times, or the biomass was increased by 2 times while the energy stayed the same,
Yes,
basically.
yes, that's correct.
Interesting. But also, I mean, your comment about the coloration of the red oak leaf lettuce is really an interesting finding to me because, I mean, uh, uh, isn't one of the challenges with vertical farms and growing pigmented lettuces like red oak leaf lettuce, isn't that a real challenge under LEDs? Or see, at least this is what I've heard or what my experience has been, because you don't necessarily get that red color, right, as vibrant as if it was outside, because it doesn't have the same exposure to the higher energetic wavelengths of light like blue or UV. But because we now have these blue diodes closer to the plants, there's sort of less um uh less that scatter less air and stuff that scatters that blue light into lower energetic wavelengths of light. So we actually maintain the blue, right? Like it, because it doesn't have a way to sort of escape and turn into something that's not blue. Am I making
Um,
sense?
yes, that makes sense. And this closed canopy lighting, along with other approaches, can enhance the coloration. As you mentioned, blue. There has been a lot of study how the end of production blue wavelength can enhance, like for example, in the last 4 days before harvest, if they increase the amount of blue, how it can affect the coloration. But the blue light generally decrease the plant diameter. So we have smaller, redder plants. And for vertical farm growers that they want to sell fresh biomass based on kilogram or pound, they want to have higher biomass accumulation and probably bigger plants. So sometimes blue uh, results in less plant diameter, smaller plants, but um, redder plants. So this is all about timing of application and the background lights that blue is part of that. How blue interact with red or other wavelengths, or how these different wavelengths negate the effect of each other. So that's another area of research that it can be one lecture by itself.
Yeah, sure. So, very interesting findings. I guess, two of the sort of follow-up questions I have to that have to do with, have to do with leaf tip burn, or one of them does anyway. So if you're only growing to 15 days, that's usually well before leaf tip burn would set in. And so I'm just thinking, especially for the plants that you are maintained, went from 250 to 400 micromoles as the LEDs got closer to the plants. It seems like those plants would be at particular risk for developing leaf tip burn once we reached day 18 or 20. Would you be concerned about that as well?
Yes, that's a real concern if we wanted to grow plants for a longer period of time. But as I mentioned, on day 15, we didn't notice any tip burn or any other issue.
Um, so could that be a continuation of this research to take these plants out to a longer distance, to a longer
Yes,
production time? Yeah.
definitely. That was first step for closed canopy lighting. It will bring more question, and it will reveal more gaps that we need to address, and also we need to investigate more on different aspects of that. Yeah.
Right. I also wonder if like maybe you hit the gas pedal early in those day 15 and then you bring it back and and reduce the light intensity or reduce the pressure on the plant to grow really fast once it's reached a certain point, and then it could still reduce the production time, but then you reduce the risk of that leaf tip burn with the new leaves beyond day 15 as
Yes.
well. Yeah.
Yes, that's good.
And so then the second question, because I have to ask it, right? Because I'm an HVAC climate control person, is, with these LED lights getting so close to the plants, the very first thing that comes to my mind is, well, how the heck am I supposed to circulate air across the plants when the LEDs are 15 centimeters away? How were you guys able to manage the temperature and humidity and airflow in the study? I'm assuming you did it at a small enough scale, so you're not, you're not in a vertical farm trying to distribute air, but did any concerns come up during that research about managing the temperature and humidity and airflow?
Yeah, as you mentioned, our experimental unit is a growth chamber, and it's very small relative to the commercial facilities out there. And we did not encounter any issue in terms of thermal control, and also in terms of air movement. And we even didn't quantify any, we didn't even develop any methods to quantify how the air movement or other things are changing at different separation distance. But definitely you are right. To accommodate closed canopy lighting, engineering solution is needed. So closed canopy, as plant scientists, we proved that closed canopy can enhance energy utilization efficiency, but we need engineering help, including yourself, to design better like thermal control, air movement. CO2 injection is important. So we want to have enough space for the fresh CO2 injection and harvesting. So these are all things because they want these bench to be accessible for the harvest or examining their plants or whatever. Um, so I think the findings of this study will help us to think more about how should be the next generation of energy efficient LEDs look like, that we would be able to practice closed canopy lighting, and how other components play an important role, including the racking system. Does that make sense to have a height adjustable racking system that we planted them and just collapse them, or getting them closer to each other and just expand them later when we want to harvest? So these are all questions that we would appreciate inputs from engineers, and we are really interested to know their thoughts about all of this. Yeah, but these are the concerns that we
Yeah.
have.
Um, with the LED lights closer to the plants, do you think that it's not just a photon distribution efficiency? I'm just going to call it that, but also um, a radiant heat effect? Because I know LEDs don't generate a lot of heat, right? I mean, that's one of the benefits and why we can get them so close to the plants, but they do get warm, right? I mean, it's not like they're cold to the touch. They're still warmer than the human hand, I think, the 98 degrees. And we know one of the challenges has been with LEDs is as growers have switched, maybe they were growing under HID lighting and now they switched to LEDs. And many of them have learned that they need to adjust the air temperature up to make up to compensate for the loss of radiant heat on the leaves, and give the plants some heat from the air, right? So we're not just chilling them now. And so I'm just kind of curious as the LED lights move closer to the plants, it does seem like maybe, there's a little bit more opportunity for some of the radiant heat to reach the leaf or the plant canopy. What do you think about that?
So that's a great point, and it depends on the LED fixture design, which I
Okay.
want to briefly explain about it. We have learned a lot about LED fixture design because we had failure using another LED system that was not designed well. So at this point, I cannot give you a list of like criteria that would be perfect for closed canopy lighting, but at least I can tell you the flaw of some LED fixtures that uh, don't come along well with CCL.
Hmm.
The most important factor is the uniformity of intensity and spectral composition. We don't want the patches of dimmed versus bright spots in terms of intensity, or patches of red versus blue versus green, because there is a cluster of red versus blue or versus green above. So as we get closer and closer, we want a great uniformity, both in intensity and a spectral composition of those fixture.
Can you give an example? Because I'm thinking about all the LED fixtures I've seen out in the world.
Yeah.
Um, and there's light bars, there's square fixtures. When I think of some of the bars, it's like white, white, red, white, blue. Like I mean, like is that what you're talking about? Like you want it to be like a consistent pattern if you had these different, yeah, can you
Yeah.
explain that a little more?
Yeah. So that's a great question. All those LEDs that we worked with in research are fixture. They are a square fixture.
Okay.
And an easy test is when you have your LEDs set at 45 or 50 centimeter distance, you can have a white piece of paper on your cropping area. Then you see how uniform and blended the intensity and spectral composition. As you get closer at 35, 25, and 15 centimeter, we still want that uniformity to be there. If we see a cluster of red in one area, a cluster of blue, or a very dim area versus very bright area, which means that this blend is gone. As we get closer, this uniformity is not there any longer. That means we will have a very non-uniform standing crop at closer separation distance.
Oh, that is so interesting.
Oh, yeah, that's why I'm telling that the finding of this study is a guidance for the design of the next generation of LEDs. If LED
Yeah.
going to be used in closed canopy lighting in a height adjustable racks, these are something that should be uh, taught and keep in mind ahead of time.
Is that
As
only important for close canopy lighting, or would that also be important for far away canopy lighting?
I think it's important for both closed canopy and other application. For example, when we do have a study that we need to reach a very high level, but our LED system cannot reach above 400, we would think, okay, at closer separation distance, I can reach at 500 or 600. But what if I don't have a good uniformity? It means that I'm stuck there and I cannot get any closer. I think uniformity is the key for all LED fixtures, regardless of CCL.
That wow, I'm actually shocked and not surprised at the same time that LED fixtures wouldn't uniformly distribute their diodes. What has been the response of LED manufacturers to this research and to your findings and feedback?
So, so actually, the response was that this LED was not designed for that specific purpose, so it didn't
Of
work.
course.
But fair enough. But again, we worked with another LED fixtures that we had, and it was not again designed for our purpose, but we could easily use that because they designed very well that like every all criteria that we were looking were met there.
So those were only two companies, but there's a lot of LED companies. So have you been trying to get the word out? And if not, I'm going to help you get this word out right here. This is going to be a clip we're going to post because I want all of those LED manufacturers to know that this is, an issue that you found and that they could help them improve their not just their fixture and make their customers more satisfied, but could also improve efficiency overall. Photon efficient. What is it? Photon capture canopy. I wrote it down. Canopy photon capture efficiency.
Yes, that's correct. Yeah, I mean that's another interesting area of research that I have planned to establish. I mean, I already have established communication with some LEDs company, and we are working with them. But in future, in a bigger project, I want to collaborate with them and also to work with their different LED fixture design and the lighting map, illumination pattern. All of them are under one umbrella that we can address all of these questions easily.
Yeah, if I were a lighting manufacturer, this would be really exciting, especially as a way to move the industry forward and maybe even, produce a product that my competition isn't producing as well. I don't know. I feel like this is a huge opportunity for the industry. I had no idea this was an issue. Um, so, just to kind of wrap up the close canopy lighting study. So you also added curtains, right? Or a way to along the edges of the rack. So can you talk about that and why you looked at that as part of the study as well?
Yes, so we decided that even when we practice closed canopy lighting, still some photons are escaping from the growth compartment at the closest separation distance that we can be. That's why we decided to test a curtain. We had some reflective curtains around cropping area, but rather than 15 centimeter, which was the most efficient distance, we went with the 25 centimeter because we wanted to have good air movement. We were adding another layer of complexity to the whole setup, 15 centimeter and curtain. Then we needed to be worried about air movement. So at 25 centimeter, and it was interesting that the combination of reflective curtain and first scenario, which was the lower light intensity at 25 centimeter, did not result in the higher biomass, but the combination of reflective curtain and second scenario, which at 25 centimeter, I cannot recall the exact ppfd, but it was close to 300. So adding reflective curtain results in the higher biomass production because some of those photons were escaping. So they reflect with their, they bounce with the reflective curtain and they reflect back to the cropping area rather than escaping from the cropping area.
Did you mostly see yield increases along the edges where the light would have immediately reflected back into the canopy?
No, because those photons that were supposed to be lost from the edges, when they bounce back and reflect, they would be somewhere in the middle of the tray rather than on the edge itself.
Okay.
I think based on the physics law that I don't know.
Yeah.
The same angle of incident would be similar to the angle of reflection, although that works on the mirror and very reflective, but still we think that it works in the reflective curtain that we had.
Okay. So now adding reflective curtains really challenges me to move air and deliver CO2 and all that kind of good stuff within that canopy. So first close lights, oh no, and now we're gonna enclose our racks. Oh my.
Yeah, but there should be an engineering solution, isn't there? I mean, we
I
know that
mean, yes.
some of the people started working and thinking about it. So, and there have been like conducting studies to quantify how the air movement is working, but not specifically linked to the CCL study.
Yeah, yeah. Interesting. Okay, so that thank you so much for doing that research. I'm curious, what advice do you have for growers to increase their lighting use efficiency that might not, include lowering their lights down to the plant canopy level? Like what can they do right now or in the near future with maybe a low cost investment if they already have a racking and lighting system in place?
Um, that's a great question. We believe that closed canopy lighting has a near-term benefit for growers, and they can easily set their light closer with the dimmability capability of the LED lighting system. They can dim them down and save significant amount of energy. In this specific study, we addressed the photon spillage or photon waste beyond the cropping area. But when plants are spaced out on the cropping area and we want to keep them longer for a more mature stage, there is still a specific waste on the cropping area during the early stage of development when photons are falling on the space rather than on the plants. And when the respacing and transplanting is not the case. We also addressed those issues in two other works that they are very well connected with closed canopy lighting. One of them is targeted lighting that is published by one of the former students in our lab, that there are individual engines on top of each plant rather than having tubular type or just randomly scattering LED engines all across the bench, which again, it could save significant amount of energy. And in another study that we submitted recently, the combination of that targeted lighting, one beam on top of each plant, and closed canopy lighting, closer separation distance and targeted lighting, again resulted in another energy utilization efficiency strategy that we call it focused lighting, which I really like to talk about you in future when the publication is out. But these are the strategies that I talk about. But for growers at this point, if they already have a setup and they already have LEDs, what they should think about is canopy photon capture efficiency. Even by looking at the LEDs layout, so they can understand how much of those LEDs are being wasted, and depending on the like a stage of development that they want to have their plants. For example, let's say that they want to have baby greens from 0 to day 15 or 18 or 22, or teen greens that even go further, or mature greens. Maybe densely populated baby greens as a lawn of baby greens would help them to use photons wisely rather than spacing them out. Or on the other hand, broadcasting seeds sometimes might not be a good solution because they are wasting a lot of resources on the seed as well. So I think in general, finding the best seeding density based on the stage that they want to harvest would be something that they can do at the moment with the existing lighting and racking system that they have.
Interesting. Yeah, I mean, it seems like uh spacing, plant spacing, we can improve efficiency a lot if we didn't have a lot of empty space, right, between planting locations. And I mean, I guess they could always install reflective curtains along their racks, though they would need to consider how they're going to move air under there. Do you think that there's any benefit to having reflective curtains for a period of time and then take them away? So maybe from, let's say they want to grow mature greens for 30 days, like maybe have the reflective curtains for day 0 to 15 when airflow isn't as critical to help with leaf tip burn and to help with the development of the plant and movement of CO2. And then maybe strip those curtains away on day 15 and really get good airflow through there. And that's when I would assume that's when it makes the biggest difference to add carbon dioxide to enrich your plants once they've reached a certain maturity level.
So based on our findings, it really depends on the background PPFD that they have. So if they do
Mm.
high PPFD, which is the second scenario of closed canopy lighting, it works well in combination with reflective curtain. But if they are using the lower light intensity close to 200 or 250, that might not be very helpful to even have the reflective curtain, and it may even impose more like restriction in terms of air movement and CO2 injection.
Yeah. Do you think it's most effective at the higher at the higher PPFD just because the beam of light is more intense that it can like bounce off that reflective curtain more strongly? These
Mm,
are not lighting terms whatsoever.
yeah, because I think it's very simple. I mean, it's a very simplified answer to say that, but I think more photons are supposed to escape, and then they hit the reflective curtain and bounce back to the
Oh, yeah, yeah.
the higher light intensity. Yeah.
That makes sense too. That makes sense too. Um, so how if you were to continue this research, and maybe you are continuing this research, what are some of the next steps or the other variables that you would want to study? You've mentioned a couple during our conversation. I'm also really curious about the plant type. And I know we've seen a lot of different studies, especially coming out of the Optimia group, that have shown that some cultivars respond this way and other cultivars respond a different way. Is that what your expectation would be for this study as well? Or do you think that all plants would respond positively with closed canopy lighting?
Mm, I think all plants would respond similarly to what we have right now for the red oak leaf lettuce rushi. But still, there might be cases that there might be specific issues linked to a specific species or cultivars. For example, the air movement. Maybe Rushi didn't have any issue with the air movement or thermal control or something else, but others might be more sensitive. So I really like as the next step of this research to stay more focused on the issues that comes with like CCL, those things that should be accommodate to be able to practice CCL, like the airflow, air movement, CO2 injection, and how the whole setup, like how the bench length would be a factor. If it's a very long bench, that like CO2 injection need to be very harsh or air movement should be higher to so I think it's getting harder when we are dealing with longer bench to deal with the air movement and thermal control. I may be wrong in this thing, but I think I want to deal more with all the issues that come after we practice closed canopy lighting and try to find a way to solve those.
Right, right. Um, Carrie and I have talked a little bit when we were in Japan about working together with some of the extra time we have with Optimia, and maybe it's another grant on integrating the airflow and the climate management into a future study with you. So
Okay.
that would be really fun. I'd love to do that with
Yeah,
you guys. Yeah.
yeah, sure. We would be happy.
So I think we have many other topics that I would love to discuss with you. You were talking about focus and targeted lighting, and that research hasn't been published yet. So I'd love to have you back on the podcast to talk about the other research findings that you've had in recent years. I just want to end with the question, what do plants crave from lighting?
Okay, I think plants crave our attention.
Oh, yes.
Yeah. So, as plant scientists or growers, we need to know plants' physiological background and determine their needs based on a specific stage of development. We call this phasic optimization. At each specific stage of development,
Mm,
plants have specific needs, and we need to determine the optimal or near optimal condition for that specific stage. Plants are so dependent on us to provide them with a good environment. And I think it's not only one factor, it's always a combination of different factors which plays an important role, like CO2, lighting, different environmental inputs. So in general, plants crave our attention.
I love it. I love it. With that in mind, what are your thoughts on artificial intelligence? If plants crave our attention, can computers and software and uh artificial programs, can they give plants the attention that they need, do you think?
I am very new to the area of artificial intelligence, and I definitely need to self-educate myself in that regard. But I think they would help to some extent. I mean, when it comes to programming, if we decide through experiments that these are the optimal condition, and then define that optimal condition and ask the AI to adjust those when the sensor are telling us that it's time for example, to adjust the light or CO2 or relative humidity or any other environmental input, that's helpful. But I think I don't know many aspects of artificial intelligence, but I think it would help to some extent. Yeah.
Yeah. Because even when you say, the optimal conditions for every phase of the plant development stage, um, I often think about cannabis and how growers grow different stages of plants in different rooms and give them different conditions, whether they're, you know, fresh cut clones or vegetative or flower. And even within flower, there's sort of multiple phases. And then, but when I think about lettuce, in some ways, it's not so obvious about what the different phases of growth are. We talk about baby, teen, mature, so and germination, right? And so maybe there's those four phases. And when AI and just what you were saying, I wonder if it could help us with those sensors and that feedback more closely define what those phases are for each cultivar, each type of plant. Or maybe we have it figured out. Or maybe it'll find a new phase that we didn't even realize.
Yeah, but I mean, in terms of resource utilization efficiency and specifically energy utilization efficiency, I think we need to determine ourselves that, for example, at the specific stage, which is the lag phase, which is very long for lettuce, like in the first 10 to 11 days. They are very small seedling that they need the minimum resources to survive. Why would we provide the same light recipe from the beginning to the end? If
Right.
the target ppfd is 250, let's say, we don't need to provide that from day zero. We can provide a different intensity with different spectral composition during the lag phase, and then when plants move to the exponential phase that they are very demanding, we need to upgrade and move to the next level of environmental inputs. And then when they reach the plateau phase, which might be close to the harvest at a mature stage, again, they are not going to use resources very efficiently. We need to cut them back to the more lower resources being provided. So that's what I meant, but what I mean, but still there is a lot that needed to be investigated, and different experiments should be set up, different studies, and all those outcomes and outputs should be fed into a model that AI can use that successfully.
Great answer. All right. So that's the end of the official questions. So now I have a few rapid fire questions is basically what I call them. So they're meant to be quick responses. If you want to expand on anything, then you definitely can feel free to. All right, are you ready?
Yes.
Okay. Are plants introverts or extroverts?
Extroverts.
Okay. What have you learned from plants?
Oh, um, plants are so dependent on us, and we need to pay a lot of attention to them. When we observe them carefully, it's as if they are talking to us.
Mm,
They're telling us what they need, and if they're not doing good or they need a different environment, they are talking to us.
I love it. A lot of people that I've interviewed have mentioned, have made a comment about plants talking or screaming or somehow communicating with us with
Oh yeah.
the language. We just have to pay attention, right? What is the worst advice related to lighting that you've heard or been given?
Mm, Actually, I cannot recall any words.
No?
No, no, because I have been under great supervision that would never let me go wrong at lighting. So,
That's awesome.
yeah.
What is so even like what is the worst advice someone could give a grower about lighting? What if we twisted it that way?
Um, my mind is set somehow that I cannot think about words.
Okay, that's okay.
I'm saying a very honest because I know it costs a lot of money. So,
Oh, it does. It does. Maybe that's the worst advice is that you need more lighting, but you don't necessarily need more lighting. You just need better lighting or closer lighting.
that's true.
Um, what crop do you want to see grown using CEA in the future?
Mm, So, when it comes to resource use efficiency, some high value crops should be grown because in CEA there is a lot of investment. We are investing a lot to keep all environmental controls under to keep all environmental inputs under control. Um, and high value crops should be grown. I think I like to see some like more of like a strawberries or some fruits produce in CEA. But I know that in most cases, when it comes to the CEA production compared to greenhouse or conventional outdoor production, they cannot compete very well. So those should be a very high value produce in future of CEA.
Can CEA feed the world?
Yes, definitely it can contribute to the food production system if the profitability issue is solved.
Yes. Fair enough. All right. Well, that's it.
Okay.
Fatemeh, thank you so much for the interview and for talking to me about your research. Even though you're not an engineer, I really appreciated the technical conversation around the LED light and how it's built and designed and uniformity. You know, I've talked to a lot of people about lighting and nobody has ever brought that up,
Okay.
which is kind of interesting to me. So, you know, it's a lot of it is focused on an intensity or focused on a, you know, a spectral quality, but not so much about the technology itself. So I appreciate those insights. Thank you.
Yep, I'm glad to hear that. Thank you.
Yeah. All right. Well, have a great rest of your day. And yeah, we'll schedule another one soon when you have your other research published.
Sure, sure. I
All
would be
right.
happy. Thank you for having me.
Thank you.
Bye-bye.
Bye. All right. That's it. Good timing.
Thank you. I waited.